Welcome to this explainer. Today, we're exploring algebraic identities, literally seeing the math. We're diving straight into the Class 9 Chapter 4 material, and let me tell you, we are going to completely flip how you think about abstract math formulas. No rote memorization of random letters and numbers here. Nope. We're transforming these abstract equations into literal, visual puzzles. Stuff you can picture, pull apart in your mind, and actually solve. So if you've ever stared blankly at an algebra problem and thought, okay, but what does this actually look like? Well, you are in the exact right place. Let's get into it.
We're kicking things off with a pretty wild mathematical mystery. So, what happens if you take three consecutive square numbers? Think of any three. Just to make it easy, let's grab the first three. 1, 4, and 9. Hold those in your head for a second. You've got your smallest square, your middle square, and your largest square. Now, what do you think happens when we start messing around with them?
Let's just follow the logic step by step. Step 1. Add the smallest and largest squares. 1 plus 9 equals 10. Simple, right? Step 2. Subtract twice the middle square. Our middle square is 4, so twice that is 8. Step 3. 10 minus 8 gives us exactly 2. Now I know what you're thinking. Come on, that's just a fluke for those specific numbers. But actually try with bigger ones, like 25, 36, and 49. Add 25 and 49, you get 74. Subtract twice 36, which is 72, and bam, the result is 2 again. It's wild, but this works for literally any 3 consecutive squares. It's not magic, it's a universal pattern.
So why does that trick work every single time? Well, we have to look at the definition of an algebraic identity. It's an equation that is true for all values of the variables occurring in it, unlike a standard equation which is only true for some. Think about a regular equation, right? Like x squared minus 1 equals 24. That's highly conditional. It only works if x is exactly 5 or negative 5. But an algebraic identity? It's universally true. The consecutive square trick we just played with happens because of an underlying identity. It literally doesn't matter what numbers you plug in, the very architecture of the math guarantees that outcome.
Now things get really interesting when we prove a famous identity by literally cutting up a 2D square. We're talking about the classic identity for a plus b whole squared. But forget the letters for a second, and just picture the physical geometry of partitioning a square of side a plus b units into smaller squares and rectangles. We start with a line segment made of 2 chunks. One is a units long, the other is b units long. We use that line to build a massive square, so the total side length is a plus b. Inside, it naturally divides into 4 distinct rooms: a large square, a small square, and 2 identical rectangles.
The absolute coolest part here is that the total area is exactly the sum of its parts, a squared plus 2ab plus b squared. Instead of blindly trying to memorize a string of letters for a test, you can just look at how it's physically built. That large square is literally made out of 1 a squared block, 1 b squared block, and 2 ab rectangles. So a plus b whole squared has to equal a squared plus 2ab plus b squared. It's not some abstract formula, it's a literal floor plan.
And this naturally brings us to visualizing the flip side, a minus b whole squared, which we can see by subtracting areas from a larger square of side a. It's the exact reverse approach. You start with this massive square with a side length of a, meaning the total area is a squared. But we only want the specific square representing a minus b. How do we get that? Well, we physically chop off the extra rectangular pieces we don't need. Once you subtract those specific areas, you are left perfectly with your a minus b squared block. The algebra is literally just mirroring the physical act of removing area.
Okay, let's switch gears a bit and look at the factorization of x squared plus 7x plus 12 using a rectangular arrangement of algebra tiles. Factoring quadratics can be so incredibly frustrating if you're only staring at numbers. But what if we treat the expression like a literal bag of physical puzzle pieces? We can use these algebra tiles to take something complex and turn it into a simple game of fitting shapes together.
So we break down the tiles for x squared plus 7x plus 12. Imagine dumping our pieces on the table. We've got 1 large x squared tile, 7 rectangular x tiles, and 12 small unit tiles. Our one and only job here is to arrange every single piece into one perfect solid rectangle. No gaps, no leftovers. And to make the corners line up perfectly, those 12 little unit tiles naturally have to lock into a 3x4 array.
Once that puzzle's built, the factors are just the side lengths of the new rectangle, x plus 3 and x plus 4. It reveals itself instantly. You just measure the edges. The top edge is our x length plus 3 unit tiles, so x plus 3. The side edge is our x length plus 4 unit tiles, making it x plus 4. This is a total game changer, right? Factoring an abstract algebraic expression is literally the exact same thing as finding the physical dimensions of a rectangle. You aren't just crunching abstract math, you're essentially doing geometric construction.
So, what happens if we take this into the third dimension? We've totally mastered flat squares and 2D rectangles by now, but how on earth do you visualize an identity raised to the power of 3? Like, what does a plus b whole cubed actually physically look like? Well, picture splitting a large a plus b cubed block into 8 smaller cubes and cuboids. When you raise a plus b to the third power, you're not just sketching a flat shape on a piece of paper anymore. You are constructing a solid 3D object. And just like our 2D square had 4 internal rooms, this large solid cube physically fragments into multiple distinct geometric building blocks. Let's quickly compare expanding in 2D versus 3D. In 2D, area expansion results in 4 flat puzzle pieces. But in 3D, volume expansion results in 8 solid blocks. We're calculating volume now. Expanding an algebraic cube literally just means adding up the physical volume of the solid chunks that form it. When you pull that big cube apart, it breaks down into exactly 8 solid 3D pieces.
Let's take an inventory of these 8 solid building blocks. First, you have one large cube with a volume of a cubed. Tucked away in the corner is one small cube with a volume of b cubed. To fill the gaps, we get 3 tall cuboids with a volume of a squared b, and finally 3 wide cuboids with a volume of ab squared. Just by counting these solid blocks, we instantly reveal the expanded formula: a cubed plus 3a squared b plus 3ab squared plus b cubed. It's such a powerful, undeniable visual confirmation of the math.
And hey, these geometric rules are definitely not just some modern classroom theory. There's historical text explaining Sridharacharya's 750 CE method to quickly compute squares. Over 1,000 years ago, this brilliant mathematician used these exact identities as a mental math hack. He used the identity a squared equals a plus b times a minus b plus b squared to crunch massive numbers. Say you want to find 55 squared without a calculator. You just do 55 plus 5 times 55 minus 5. That's a super clean 60 times 50, which is 3,000. Then you just add the square of your offset, 5 squared, which is 25, and boom, 3,025. He was literally using the geometry of identities to shortcut arithmetic centuries ago. How cool is that?
So, bringing it all together, here's the complete summary list of all algebraic identities studied in the chapter. Normally, you might look at a list like this and just feel completely overwhelmed by a wall of meaningless text. But now you know the secret. These are absolutely not arbitrary rules to just memorize by rote. Every single equation here is actually a universal blueprint for a physical shape. They're basically instruction manuals for calculating lengths, areas, and volumes.
So how would you use Sridharacharya's 750 CE method to easily solve your next math problem or even visualize an identity in the fourth dimension? That's the challenge I'm leaving you with today. The next time you're faced with a complex equation, are you going to just memorize the letters, or will you actually look closer and find the shapes hiding inside? Try using that ancient math hack in your daily life to calculate a tip or a measurement. And if you really want to stretch your brain, well, we've seen area in 2D and volume in 3D, but how on earth would you use these exact same principles to visualize an identity in the fourth dimension? I'm going to let you puzzle over that one. Thanks for diving into this with me.